Okay, this is the first lesson out of chapter 24. And chapter 24 is actually about magnetism. But magnets, what we're going to understand about them, we understand fairly quickly when it comes to magnets. I'm going to give you today, just an overview of magnets and magnetism, and we have to understand the magnetic field. And unfortunately, that's something you almost need to see, would be what a magnet does. We would have done an activity in class where we would look at the magnetic field. I'll try and show it to you here, and most of you will be able to understand that. But the idea of a magnetic field around the magnet, very similar to the electric field around an electrical charge. But what I want to do today is just introduce magnets themselves. I want to give you just a little brief history and then some properties of magnets. As far as we know, when we talk about the history of magnets, we've known about magnets for about 2,000 years. And as far as we know, the first people to discover magnets were Greeks, and they lived in the province of Magnesia. And if you can't see where magnet and magnesia are similar, I can't help you. Magnesia, the magnets are named after that province. And what they found was there were rocks that attracted metal, attracted iron particularly. And that, of course, is what a magnet is. Now, you might ask, how in the world did those magnets form? Well, there are naturally occurring magnets, and we'll talk about that in a few minutes. The first people we know to use magnets were the Chinese. The Chinese were using magnets as compasses. A compass is a suspended magnet, which allows you to know which direction you're heading, because a compass will always point north. So if you're heading one direction, the compass says you're going, the north is this direction, you can figure out which direction that you're heading. And as far as we know, they had compasses about 900 years ago. So compasses, magnets have been known about for 2,000 years. 900 years ago, they were being made use of by the Chinese. And then in the year 1600, an important book was written by a man by the name of William Gilbert. He happened to be the Queen Elizabeth's personal physician in England. He was a scientist, and he wrote a book called De Magnete, which we would say is the magnet. And in there, he talked a lot about the properties of magnets, but he also began to postulate that there might be a connection between electricity and magnetism. And he also postulated that the Earth had a magnetic field, and that's what was causing compasses to work. So when we think about the Earth, we know that we have the core of the Earth, but what he said is there must be essentially like a big magnet inside of the Earth with a magnetic field around it. And we'll talk about that more in a few minutes. The properties of magnets are fairly straightforward. Most of you will know a lot of this. First, a magnet has polarity. We say that it has a north-seeking end, and it will have a south-seeking end. On your compass, if you have a magnet, an old magnet, they will often mark N and S. It's called the north-seeking end, because if this is the North Pole of the Earth, a magnet will point toward that. By the way, we call this the North Pole of the Earth and the magnet is north seeking, which this is a little bizarre. You have to think about this a little bit. That means that technically this end of the magnet is south and north, because that's our second point, is that opposites attract and like repel. So if the north end of my compass is attracting to the south or to this pole, then technically this is the south-seeking pole of the Earth, and my magnet will be being attracted to that opposite end. I should have mentioned, when we say it has polarity, every magnet has polarity. An electrical charge, this can be one of the fundamental differences between electricity and magnetism. I can have a single positive charge. I can have a single negative charge, but I cannot have a magnet, we would say, with a monopole. Now, I read an article not too long ago that said they have isolated a monopole meaning just a north or a south. But I haven't seen any follow-up on that, so I don't know if that's true or not. But for the most part, for us, if I was to take a bar magnet and break it in half, I do not get a north end and a south end. I now have two magnets, each with a north and a south. So if I take my magnet, and this is the north end and the south end, and we break that, I now have north-south, north-south. If I break it again, I have north-south, north-south, and so on. In fact, if you took that magnet and crushed it and made it into little tiny filings, it's going to end up having, every single one of those will be a little tiny magnet. So you cannot isolate a magnet. Opposites attract, like repel. And then third, there are actually two different types of magnets. One is called a permanent magnet. And permanent doesn't mean permanent like it can never be changed, but a permanent magnet holds its magnetism. For a long period of time. Some of you, I'm sure all of you, have magnets that are on your refrigerator, for instance. And those magnets would be magnetized for long, long periods of time. I have two magnets here. This is a magnet and this one, and these have been out in my garage for years, and they still have their magnetism. And of course, they're able to cause that to jump up there. Permanent magnets primarily are made from iron, nickel, and cobalt. Although there are a few other rare earth metals, neodymium is one of them, that if you mix those in with these, make for some very, very, very strong magnets. Number 4, there is something called a temporary magnet. And a temporary magnet is something which is magnetized when it is in a magnetic field. And I should just mention, when we talk about a field, that's a region in space that's being affected. So this magnet is affecting space around it, and it will be attracting to other things which are magnetic. Now, what happens is if I take some paper clips, in fact, if I do this, I get all of these paper clips. Now see this one hanging from the bottom here? I don't know if you can see that. This right here, that paper clip is magnetized. And it's magnetized and it's attracting the one below it. What's happening is this is a temporary magnet. If I was to take these, let me see if I can do this real quickly, and I start hanging magnets on here, not magnets, paper clips. Some of them want to pull back up because that magnetic field is so strong. Oops, that one didn't work. All right, now if I pull, sorry about this, it worked so well before. If I was to pull these off, that will stay magnetized for a little bit of time, even though it's not with the magnet. But give this a little bit of time and eventually that one will drop off and then it won't be magnetized anymore. So I don't know if you can see that well, but that is called a temporary magnet. And then, of course, a compass is when we take and suspend a magnet. Now, a question often comes up at this point. How do you make a permanent magnet? There's a number of ways to make a permanent magnet. I knew a teacher, he was a junior high teacher. At the beginning of the year, he took an iron rod. He lined it up in the direction pointing north, toward magnetic north. And every day he would tap on the end of it with a hammer. Every day in class, he would walk in, he would give 5 or 6 taps. And by the end of the year, that bar had a slight magnetic, was slightly magnetic. And that helps us to actually understand what's happening with a magnet. And that is, and this is beyond the scope of this course, but we believe that there are called domains. There's regions inside of the iron. Every iron atom is essentially a little tiny magnet. Because the electrons moving around create a magnetic field. And there are certain materials that are magnetic, iron, nickel, and cobalt are them. And our thought is that if I think of all of those magnets, think of this as pointing north. Every single one of these will be pointing in a different direction. So if iron cools very quickly, molten iron, these magnetic domains, those individual atoms that are magnetic, will be pointing in every direction. But my friend, my fellow teacher, every time he hit this, some of these will break loose and then they will be oriented more in the north direction, if we think of it this way. I should have done it up, rather. And over time, this becomes slightly magnetic. Now, there's a better way to make a magnet, and that's to take and put a piece of iron into a strong magnetic field. So if I take a nail, that's supposed to be a nail, I didn't do a real good job, and I take and put it into a very strong magnetic field, I will essentially do the same thing, and you'll get all of the magnetic fields to line up in the same direction. You say, well, how do you create a magnetic field? Turns out that it's real simple, and that'll come in the next section, but you can create a magnetic field with electricity. In fact, a coil of wire will have a magnetic field through the center of that coil of wire. I had a junior high student who created a little magnetizer, and he did it by taking a plug and taking the wires and stripping these wires. So he stripped the wire right here. There's 2 wires coming off, and he basically would wind these wires around a nail, bring this back up, and then he was smart enough to know that if you do that, you're going to short out the house. He put a little piece of aluminum foil in here. So I don't know if you can see it. This gets plugged into the wall. The current flows through here, and that aluminum foil burns out almost immediately. And he would take and plug it in. There'd be a flash, and his nail would be magnetized. And that's all you really have to do. You'll have bice screwdrivers that are magnetic and magnetized. Now, let me talk a little bit about the magnetic field. You guys have an advantage because you've already looked at electrical fields. If I take a bar magnet north and south, and I put a compass. A compass will always point toward the north. If I take and put a compass here, that compass right here will point like this, and here it will point away from it. And we have the beginning of a magnetic field line. What's going to happen if I put the compass right here? What's going to point this direction and this way, whereas here it's going to point out this direction. But just like electric fields, in fact, think of this as when we had a positive and a negative. Actually, negative and positive would be better. And if I put a little positive test charge, that would go this way. Positive test charge would go this direction and out this way. But if I put a positive test charge here, it would be attracted, or better yet, a positive test charge here. If you remember, it went up and it came back around like this. Something very similar is going to happen here. This compass is being pulled here, but it's also being pushed away on this side. And here it's being pushed away and being pulled. Better to look at it that way. And so this will end up going around like this. One here would go out like this. And you get what are magnetic field lines. So we actually would do that in the class. We would create it. You may have seen it up on top of my board. And the idea would be that if I was to take and put a compass right here, that compass would line up this direction. It's really cool. Once you draw your magnetic field lines, you can take your compass and put it on there and trace it around. And the arrow, this is my compass, it's normally going to point north. I put it in here, and no matter where I put it here, it's going to point in that direction as it goes around. And we actually create those in class. Those are called magnetic field lines. It's very, very similar to the magnetic field lines of the electric field lines around electrical charges. And again, it's very similar to what you would get with a plus and a minus, because we have the north and the south. Excuse me. Just clearing my throat. I'm not sick. So that is a brief introduction to magnets. What I'd like you to do is read that first section, 24.1, and then we are going to do problems 1 through 4. Those are practice problems, but they're thought problems, and then 33 through 38. And that will be our first assignment out of this section.